thought. This is a motocross adventure bike, and you can notice that it has very large shockers. Now, these bikes are designed to take extremely heavy impacts again and again without damaging themselves or their riders, and they accomplish this with the use of these shocker springs. Have you ever wondered how do they calculate how long the spring has to be, how thick the spring has to be, how much should it travel back and forth in order to have optimal performance for the bike and the comfort of its rider? In order to understand these things, we need to understand the spring force in detail, and that is what we will be doing today. So, springs are special in the sense that the way in which they exert forces and forces are exerted on them are a little different and actually a bit contrary to our thinking or intuition. For example, look at this diagram. You can see here that the spring is at a mean position, that is x equal to 0. At this position, the spring is neither compressed, so we are not squeezing it, nor is it expanded. It is just sitting there at rest, very happy. Now, if we were to apply a force to pull this spring to a larger than original length, the spring will apply an opposite force to this. So here we say that x is positive. We are increasing the length of the spring. The displacement is considered positive, but the force exerted by the spring is clearly negative. It is opposing the stretching that we are inflicting on it. On the other hand, if we were to push the spring inward, if we were to compress the spring, the displacement would be negative, x is negative, but the force exerted by the spring is positive. It is trying to expand back to its original shape. So in both of these cases, we note that the spring force, the force exerted by the spring, is always in opposition to the change in its shape. The spring force is trying to contract when we pull it apart, and it is trying to expand when we push it closer together. For this reason, we say that the spring force is always acting in the direction opposite to the displacement of the spring. We can write this mathematically as Fs is equal to negative of Kx. The negative sign tells us that the spring is always trying to oppose any change in its shape. We will understand the role of K shortly. So here is a diagram that tells us the graphical relationship between a change in the length of the spring and the force being exerted by the spring, the restoring force. You will notice here that for positive displacement, when we are increasing the length of the spring beyond its normal size, the force applied is negative and it is clearly linear. On the other hand, when we try to push the spring in, here we can see that even though the displacement has become negative, the force exerted by the spring is now in the opposite direction, the positive direction. Another thing to notice here is that the area of this triangle comes out to be half times k times x square m, where k is the ratio of the force exerted by or on the spring to the change in its displacement. So it is a pure number. In this case, we notice that this formula gives us some more insight into how the spring is able to store energy. We will see how shortly. So the term K is called the stiffness of the spring. The more K increases, the stiffer the spring is. So if the value of K is high, it takes more force to pull or push the spring from a given point of rest. So a less stiff spring, a spring which is easy to pull or easy to push, will have a smaller value of K, and a stiffer spring which is difficult to pull apart or difficult to compress will have a higher value of K. So what is the work done by the restoring force here? Remember that whatever force we are applying, the spring is reacting with the restoring force. So the shape of the spring is changing. The displacement of that point of interest is changing in response to a force. So some work is definitely being done. Now, we can calculate a tiny amount of work done for moving the spring by a tiny amount of displacement, and we can integrate that small amount of work over the entire displacement of the spring. So if we write this mathematically, we can say that the work done is equal to the integration of the multiple of force with this tiny increment in displacement over the interval x1 to x2, where x1 is the starting position and x2 is the final position. Since we are dealing with a relaxed spring which is not under any force, we can consider x1 to be equal to 0. So we also know that F in this case is actually the restoring force. So we can rewrite this equation as W is equal to Fs times dx, that is the restoring force multiplied by the differential displacement, the tiny displacement, and the limit changes to 0 to x, where that x is the displacement of the spring from its original position, which we call 0. We already have learned that the restoring force is given as Fs is equal to negative kx. So we can substitute this value in the prior expression, which gives us work done is equal to 0 to x integrated negative kx times dx. If you solve this equation, we get an expression for work done that is equal to negative half kx squared. We can classify this as the elastic potential energy of the spring. So that expression comes to Vx is equal to negative half kx squared. Now, before we move further, there is an important little detail that we have to understand first. With regards to the types of forces, there are two major classifications. We can call them conservative forces or non-conservative forces. Let's understand what is the difference between these two terms. Let's look at this example. Here we have a businessman who is clearly quite smart. He had to outsmart the shark somehow to get to this point from this point. So what did he do? He squeezed down the spring and then released it, and the spring in turn threw him all the way to the other side. Now, this could not happen on its own. In order to achieve this, the businessman or this gentleman here would have to push the spring down. He would have to perform work on the spring, and when he released the spring would catapult him across the chasm and he would escape from the shark. So the spring was in a way returning the energy back to the businessman. Whatever energy he used to compress the spring was given back to him when he jumped over this chasm. So this is an example of a conservative force. The work that you have done in the system gets stored in the system in such a way that we can recover it later. But what about a non-conservative force? So here again we have two poor businessmen who are trying to create a bridge across this chasm here again, but there is an important difference. They are clearly doing work, they are clearly expending energy. This man is pulling the boulder and this man is pushing the boulder. They are applying a force, they are causing a displacement. But the important thing to remember here is, in the previous case, the work done by the businessman was getting stored in the spring in the form of elastic potential energy. No such thing is happening here. Even though they are clearly applying work on this object, once they have bridged this chasm, once the object has stopped, its energy is now again zero. We are not considering the height here, we are not considering the gravitational energy here, because the height of the boulder is not changing. Once this man stops pushing, once this man stops pulling, the boulder comes to rest and its energy again becomes zero. So even though clearly work was done in this case, the force of friction here was a non-conservative force, and that energy was not given back to these two men once they stopped applying force, once they stopped working on the boulder. Now, because spring force is a conservative force, because the amount of work you do on the spring gets stored in the spring, spring force also has another interesting quality. If you were to move a spring from point A to point B, you would cause a change in its elastic potential energy. The change in its energy would depend only on the initial and final locations A and B. In other words, the spring does not care how you got from point A to point B. You could apply any path, any choice of path to come to this point, but in the end, the change in the spring's energy would depend only on the difference, the displacement between point A and point B. This is a quality of all conservative forces. The work done under the influence of a conservative force does not depend on the actual path taken by the system, but only on the initial and the final locations of the system. So in this case, as we have seen again, the change in work can be given as the difference between the initial and the final displacement of the object, and the integral of the multiple of negative kx with dx. This again gives us the difference in energy. If we solve this equation, we come to a new result, that is half kx square max, that is the energy at maximum displacement, is the sum of two different energies. One is the energy due to its elastic potential energy and the energy due to its movement. At equilibrium, x is equal to 0. It is neither stretched nor is it compressed. So at that location, the potential energy of the system becomes essentially 0. So we can come to a new result, half kx square max is equal to half mv square max, which tells us that V max will be equal to root k upon m x max, where k is the spring constant and m is the mass of the spring, where x max is the maximum displacement of the spring. A little more about conservative forces. Consider this car which is trying to accelerate on a flat road by spinning its wheels really fast. In fact, the wheels are spinning so fast that the tires are heating up. You can actually see smoke here. But the question is whether the work done in spinning these wheels at high speed is getting stored in the vehicle in any way that can be recovered easily. And the answer is no. All the energy of these spinning wheels is being converted by friction into heat energy. And while the conservation of energy is perfectly valid, we are not going to be able to extract this heat energy to make this vehicle move faster. So in this case, the vehicle is moving or performing work in a non-conservative field. In this case, it is friction. On the other hand, the watch spring of a clock is an example of a conservative force. So when you wind up the clock in that watch, it is storing the energy that you expended in compressing the spring and returning that energy back to the mechanism when the clock starts running. So in this case, we are able to recover the mechanical work that we have put into the system. So a spring is an example of a conservative force. So we understand in our day-to-day lives there are two main conservative forces. One is the force of gravity. If you were to lift an object against the force of gravity, you are storing that effort in that object in the form of gravitational potential energy. And the ubiquitous example of conservative force is the spring, which is able to store all the work that you have done inside the spring in the form of elastic potential energy. So to summarize everything we have done so far, let's look at what we have learned.
Manorama Horizon. Learning made simple.